All right. Hello. Yeah, thank you for the opportunity to speak. Yeah, feel free to stop me with questions, and if we don't get to your question, I'm very happy to chat later as well. Yeah, so I'll start by having our setting. So our setting for the whole talk will be a homogeneous variety G mod P, and I'm gonna start off with maybe an example to kind of so you have something in your mind for like what to think of for these spaces. So my example, RG is going to be SL3, and um, and then you can think about there's a parabolic subgroup inside of it, which contains a fixed Borel, which will typically, the Borel will typically be, you can just think like upper triangular matrices, and then inside of that, there's a fixed maximal torus, which is typically diagonal matrices. And so then we can think about like what happens if you take a quotient of G mod B or G mod P, like what do you get? So if you take a quotient of G mod B, you get the flag varieties. In this case, like you can think about, this is like if you have a flag variety, which is the set of these like nested vector spaces, like V1 is a one-dimensional vector space, which is contained in a two-dimensional vector space, which is contained in a three-dimensional vector space, which will be all of C3. You can represent that by a matrix where you think of, you have a basis for each vector space. So maybe if we take just the identity matrix, like this would represent, say, the standard flag where your first, the column, like the first column tells you that first vector space, the span of the first two columns tells you your second vector space, and then the span of all three columns is all of C3. And you can notice if I multiply this by some upper triangular matrix, okay, hopefully the result is not too shocking. I was like, which matrices can I multiply without messing up in front of a group of people? I think I have this one, hopefully, but someone please tell me if I messed up. But you'll notice, like, if I do this, like this matrix represents the same flag as this one, right? Like the span of the first standard basis vector is the same as the span of A0, 0, and so on. And for the like two-dimensional vector space, you can take kind of like linear combinations of the first two. So that's what happens when you quotient by upper triangular matrices. And then if you quotient by a parabolic subgroup, so something containing the Borel, what ends up happening is you kind of forget some of those vector spaces. So in this example, when you quotient by that parabolic, you sort of forget the first like one-dimensional vector space, and you're just looking at two-dimensional vector spaces in C3. And so we get, in this case, the Grassmannian two planes in three space. But in general, you can get partial flag varieties this way. So, but if you want, you can just think about Grassmannians are kind of the most partial flag variety, maybe. Okay, and so then I'll say maybe a little more about the structure of these spaces. So one thing you can do is look at the tangent space of the identities. You can look at its Lie algebra, which has this nice decomposition into root spaces. And so maybe I won't say exactly how to get the root system, but the thing to have in mind is that actually you can know a lot about these spaces just by looking at the root system. So this is the root system for SL. For SL3, there are those simple roots alpha 1 and alpha 2. Like this picture is like living in R2. Like this is an actual picture of it. And then at the center is the origin. And you can get the other roots by like adding and subtracting alpha 1 and alpha 2. And I'll also, yeah, and then another part we'll need is the Weyl group, which is generated by the simple reflection. So maybe this one I will also draw out to illustrate the reflection part. So this is the same picture. Okay, so if I want, so you might notice there's a lot of symmetry in the root system. And if I want, when I say the reflection in alpha 1, what that means is like you draw, I guess you can think about the line through the origin in alpha 1, take the kind of hyperplane orthogonal to it, and you're reflecting in this line. So like S1 of alpha 1 takes you to negative alpha 1, and S1 of alpha 1 plus alpha 2 takes you to alpha 2. So the vowel group like acts on the roots. Like that's kind of the thing that you'll need for later. All right. So, okay, so I'll also define that you can also define the vowel group more generally. So, and maybe this, I don't know, helps you believe that the elements of the vowel group are actually like matrices as well in that original big group G. And then, yeah, I'll just make a quick comment about if you're interested in not just the full flag variety, that's when you need to deal with parabolics. And so there's a vowel group associated to the parabolic as well. And if and then you can look at minimal length coset representatives of like W and then multiplying on the right by that. And the reason you need that is just to get the sort of Schubert cell decomposition of our G mod P space. So what's really nice is like you can look at, so these these BW P mod P's, these are Schubert cells, and kind of maybe the key takeaway from this part is that this gives you a cell kind of decomposition of G mod P that's indexed by these vowel elements. And you can look at, if you take the closures of those cells, you get Schubert varieties. And maybe the most important thing is that if you take the homology classes of these Schubert varieties, you get a basis for the homology. So actually, yeah, this last statement is probably the most important takeaway from this intro bit that we'll need for the rest of the talk, is that we have a really nice basis for the homology. And I'll point out that sometimes when people say Schubert class, they mean cohomology class, but I really do mean homology class for my talk. Okay, I guess any questions on the intro bit before I keep going? All right. Okay, so I'll give a little kind of background and motivation for the question I'm currently working on. So in 1961, Borel and Heflinger posed this question, like in a G mod P, like which Schubert varieties can be represented by some other subvariety. So meaning like I have some other subvariety in my G mod P, I take its homology class and it's equal to the class of the Schubert variety. So this is sometimes called the rigidity problem. Like if this is not possible for a Schubert class, you might call that class rigid. Okay, and so this is kind of a big motivating question, and this has been studied by a number of people. For example, Joskun answered this for regular Grassmannians, and then Robles and Joskun and Robles worked on this for co-minuscule G mod P's, and more recently, this was answered for more generally for partial flag varieties of type A, B, and D by Liu, Sheshmani, and Yao. So this question's been studied and answered in these cases. And that kind of leads us to Joskun kind of proposed sort of a family of questions sort of inspired by that original rigidity problem. And so one kind of set of these is like which effective linear combinations of Schubert classes can be represented by a smooth subvariety or some effective linear combination of smooth subvarieties, or just a linear combination of smooth subvarieties. So, and maybe I'll point out, yeah, most Schubert varieties are singular, so that's why you might be interested in smooth representatives. Okay, and so I think, yeah, maybe I'll point out one known result that's related by Kolar and Vosan somewhat recently. And I will highlight, so only this result is much more general. So everything else I'm saying is for G mod P, but this result is actually for any smooth projective variety. And they proved that if you're in dimension kind of less than half of the full space, then for any cycle in the Chow ring, there exist smooth subvarieties such that you can write your cycle as a linear combination of smooth subvarieties. Yeah, so this is a much more general result. So this answers that like third bullet kind of in dimension less than half. Oh, and maybe I'll also point out, in the case of G mod P, the Chow ring is the same as the cohomology ring because the Schubert cells give you an affine paving. Was that question? Yeah. So there's no positivity. Yeah, no, it's really like any smooth projector. You mean on X or? Yeah. Correct. Yeah. So, yeah, I guess so. This actually answers the more general like question of like which linear combination, yeah, can be represented by a linear combination. So yeah, correct. Yeah. Yeah. Yeah, so I just wanted to kind of highlight that related result. But yeah, all right. So, okay, so that kind of leads to, so the question I've been focusing on is which effective combinations can be represented by some effective linear combination of smooth subvarieties. And so the strategy, yeah, so the overall strategy I've been taking is, so I look for some smooth subvarieties in G mod P, and then write them out, compute its Schubert expansion, like write them out as a sum of Schubert classes, because then I can say like whatever output I get here, I know this can be represented by Y, and then I can sort of extend my results by taking effective linear combinations and kind of build the cone that way. So, okay, so maybe I'll give some examples of what things that you might look at to execute the strategy. So, so there's kind of a bunch, but so some smooth subvarieties exist, or you can look at homogeneous subvarieties, so kind of smaller G prime mod P primes. You can also look at Richardson varieties. You can also look at, like, if you do have a smooth Schubert variety, if you intersect it by a hyperplane, that will still be smooth. And if you intersect general translates of a hyperplane, that'll also give you something smooth. So these are some possibilities for what you can look at. And these, yeah, maybe I'll just point out these kind of lower bullet points. These have known ways of computing their Schubert expansions by looking at structure constants like Littlewood-Richardson coefficients. There are also some known formulas like Chevalier or Pierre type formulas for computing intersections with hyperplanes. And so the one I'm going to focus on today are the homogeneous subvarieties, and we're going to use BGG polynomials and divided difference operators to compute their Schubert expansion. Okay, I guess any questions about this question or strategy before I dive into the homogeneous subvarieties? Yeah. Are there Schubert varieties where the answer is known to be negative, or there's like nothing? Yeah, so there are. So in yeah, so like in the Grossmanians, the co-minuscule, and those, I guess, type A, B, D, in those set of papers, like there are some Schubert classes that are rigid, meaning like they cannot be represented by any other subvariety, like let alone a smooth one. So there are some Schubert varieties where we do already know, like, you know, no, you can't even represent it by any other subvariety. Yeah. So they're okay. So I'll start with step one. So we can think about like how do homogeneous subvarieties arise. So some options are, so I won't say too much about the sub-diagrams of the Dinkin diagram, but that is a way to get homogeneous subvarieties. And the example that I have there is by looking at sub-root systems. So I did a different type just to kind of illustrate that this is not type dependent, but this is a type C2 root system, which corresponds to the algebraic group SP4. And then the circling Yeah. So the blue part's the Borel, the positive roots, and then the bigger circle for the P determines the parabolic that you're quotienting by. And the green, like the green two diagonals are this P1 cross P1. So you want to kind of think about P1 as SL2 mod upper triangular matrices. Like, yeah, right there. And so in this case, we kind of have two, if you look at this subroot system, like that's an SL2 root system, and then you also have another one along the other diagonal. So you can look at this P1 cross P1 inside of SP4 mod that parabolic. So yeah, so this does get more difficult as your root systems are bigger, but the idea is inside your root system of your big G, you can look for a smaller like subroot system. And once you do, yeah, and then kind of the way you get to an actual subvarieties, the subroot system gives you some sub-Lie algebra, which then corresponds to some subgroup of your original G, which then gives you a sub variety if you, intersect with the original P. Okay, so these are kind of the homogeneous, or one way to get homogeneous subvarieties. Okay, so that means we're on to the second step of computing the Schubert expansion. So I'll say a little bit about, BGG polynomials and divided difference operators. So we'll start off by kind of recalling this result from Borel that if you look at polynomials in the roots, so the alpha 1 through alpha n are the roots, and you quotient by a particular ideal, you actually get a polynomial ring that's isomorphic to the cohomology. And that's really nice because then you can work with like if you want a cohomology class, you can kind of work within the polynomial ring instead. And then Bernstein, Gelfland show that there are these polynomials in the polynomial ring that are dual to the Schubert classes. So like meaning if I take this phi map that's the isomorphism, apply it to the polynomial, and then pair it with the Schubert class, like that's the Kronecker delta. So there are polynomials that are dual to the Schubert like homology classes. I guess maybe I'll say, the reason this is relevant or useful is because if I want to compute this coefficient in the expansion, like I want to pair my XW class with the dual cohomology class, like that's how I can extract the coefficient in the expansion. Okay, so these exist, and then even better, these are actually very computable. Like these PW polynomials that represent the cohomology classes are computed using divided difference operators. So so divided difference operators, just you take your polynomial, you subtract it with, you apply one of those reflections to your polynomial, and then you divide. So kind of the point is that it's a very doable computation. Like it's reduced to like just kind of polynomial manipulation. And then you compute, kind of the point of these theorems that you start by computing the biggest polynomial, the polynomial corresponding to your longest vowel element, and then you can compute all your other PWs kind of iteratively by applying more and more divided difference operators. And then this last bit is just that also kind of maybe to highlight the usefulness of divided difference operators, that you can compute this pairing between cohomology and homology also using divided difference operators. That's kind of the theme of this. And okay, so just to recall what we wanted, we had this homogeneous subvariety that we wanted to compute its Schubert expansion. And the thing that I worked on was to show that you can do this by taking those PWs that we just saw how to compute. You restrict it to H prime, which just means like the original roots were in H star, and then H prime is kind of the smaller one for your homogeneous or for your subvariety. And then you apply divided difference operators. Like kind of the point of this is that you can compute the coefficient by using the polynomials and then doing divided difference operators. So like it's a doable computation. And maybe for the sake of time, I will skip. I do have an example computation that's showing that you can apply this proposition to that example we saw earlier. Yeah, I guess the point again is that it's doable. Like you have some polynomial for the cohomology class, you rewrite it, and then you apply divided difference operators. Like there's nothing fancier happening in computing the coefficient. So maybe I will, end with showing just kind of what I've gotten for a particular space. So for SO7 mod P2, the maximal parabolic P2, which is the orthogonal Grassmannian of two planes in 7 space. So this is one example. What I've done is I've plotted, so the black points, like the points on the graphs are just points where I've done explicit computations and gotten like a smooth representative. And then if you take like effective linear combinations, you can kind of fill out, you can sort of conclude that those gray points can also be represented by some effective linear combination. And maybe I'll end by noticing that, so at least in this case, like in dimensions 1 and 2 and codimensions 1 and 2, so it's dimensions 5 and 6, the whole space is 7-dimensional, you can actually get all of them. Okay, I think, that's all I had to say.